Hello everybody, thank you very much again for joining us today. I am Lju Lazarevic, and like Adam, I'm also part of the developer relations team, and I'm going to be talking to you about some approaches that I've used for dealing with duplicates. So, some time ago, I was thinking about interesting data sets to play with, and I came across the BBC Good Food website. So this is, for those of you who are not based in the UK, this originally, which was created by the BBC, and there was a magazine series and all sorts with it, is a very large repository of recipes, and there's something like 200,000 recipes on there. It's huge, and they're all freely available, and you get many different recipes in different categories. So it could be by meal, by nutritional requirements, and so forth. So they have a huge number of recipes, and I was quite keen to think about, can I get at that data? So I don't necessarily want to take the recipes and things, but I was quite keen to see there's some cool things that you can do with that data around the ingredients. So things such as, can you group together similar recipes? Is there some interesting things you can do around recommendations and so forth? It's a very rich data set with many possibilities. So I was exploring this data a little bit more, and I was looking at the source code of the various pages, and I spotted this very handy JSON-esque looking nugget of data, and I thought, brilliant. I can take this data, and this data has got things such as the author, it has the ingredients, it'll have information around, say, cook time, any keywords and so forth. So it's a really nice, rich bit of information that's easy to pull out and extract. And this is something that me and my colleague, Mark Needham, did a while back, where we created some stuff to pull this data out, and we eventually pulled it into this data model here. So there's loads and loads of data, but we kept it quite simple. And the idea is that we've got recipes, so recipes at the center of our universe, of our data model. And here we've attached some information. So we've got things around, the diet type of the recipe, what collection did it come from, attaching the number of keywords associated with it, who wrote it, and so forth. And of course, the one that I'm really interested in is what ingredients are part of that recipe. And the purposes of what we're going to be doing in this session, or what we're looking at, is, as you'll see in a couple of examples we show, there are a lot of duplicate ingredients in the data set, and there's going to be many good reasons why we want to remove those duplicates. So, for example, maybe we want to do some kind of work as being able to categorize types of ingredients. So maybe we want to get a hierarchy of different tomatoes. Maybe what we want to try and do is, by deduplicating our ingredients, we can start to spot duplicate recipes, or in a similar vein as well, based on the kind of ingredients there, maybe we can start to understand what kind of recipes would be a better recommendation from somebody because it contains the same core ingredients and so forth. So there will be a huge number of reasons why we want to deduplicate those ingredients. And when I talk about duplicates, there are many. So just as an example, if we ran a query to find all of the ingredients in our data that contain the word, so basically name is the property, an ingredient that contains the ingredient name, and we look for everything that contained almond, we get a lot. So as you can see, so we've got almond and almonds, so we've got plurals going on here. We've got things like almond flakes, flaked almonds, almonds, ground almond. So we've got a lot of duplication going on. We've even got the one, for example, here we've got whole blanched almonds, and we've got blanched almonds. So we've got a lot of different things going on here. We've got a situation around tenses being involved. We've got plurals involved. We've got an additional word in as well. So we've got lots of things which come together, which may construed duplicate data. But I can't really call it duplicate data just based on my observation. It's going to be duplicate data because I will have either deliberately or inadvertently, I'll have put together a set of conditions in my mind as to what would determine, in this example, these ingredients to be duplicates. And this is going to be driven by business rules. And this is always going to be based on what questions do we want to answer. So just to give you a quick example. So in the previous slide, I said that almond and almonds were duplicates. But this is working in the example where what I'm keen to do is to simplify down the ingredients. And I'm saying in this example, plurals of words are duplicates. But for example, if you were looking at stock, so if you had some kind of stock or stock keeping, it could well be that an almond on its own and almonds could be two separate distinct entities, and you wouldn't want to group them together. So you really have to think about what business rules are going to be driving the decisions you've made to say whether or not two entities are the same. So in this example, the business rules that I've come up with when thinking about how I'm going to deduplicate the ingredients of the data here, they're going to be things around plurals. So what I'm saying is any plurals I want to get rid of because those are probably going to link to the same entity. Same with tenses. So for example, we had almond flakes, so that's in the present tense, and flaked almonds. So you've got the D at the end of flakes, that's in the past tense. So I want to get rid of those. And I want to get rid of any stop words. So for example, somebody might say ginger, comma garlic, maybe they say ginger and garlic. So I want to get rid of all the words like and, or, the, and so forth. And the reason I want to get rid of those is when I'm doing this as part of the data cleaning, because I don't see those as useful words in this context. Again, it will depend on the kinds of questions you're looking to answer in your context. I also want to try and identify things that sound similar. So this list is kind of a mix of the data cleaning rules that I'm applying, and these are both going to apply when I'm actually going through and sorting the data, which we're going to do shortly. But it's also looking at what other things I'm going to do as well, and what structures of the graph I'm interested in. So any things that sound similar, I want to group together and say they might be the same. I want to tokenize words. And the reason why I want to do this is I'm trying to remove the ordering of words. So again, almond flakes, flaked almonds. When I tokenize those and I clear out all of the tenses and plurals and that kind of thing, should match to be the same. So I want to tokenize to get rid of any ordering biases going on. And I need to think about some kind of thresholds to deal with missing words. So for example, our blanched almond and whole blanched almonds. So how can we skip those through? So just to give you an example, what I'm going to be doing is I'm going to be adding an extra node to my data model called the ingredient name. And that ingredient name is going to be tokenized version of the ingredient. It's going to have dealt with any plurals, any special symbols, and so forth and so forth. So let's think about what we're going to do next. So I'm going to be doing a bunch of steps where I'm going to do some sort of rudimentary data cleaning. And then the next stage, what I want to do is I want to be a little bit clever now. So we've done the very sort of localized cleaning of the data. And now what I want to do next is to use the graph structure to be able to suggest additional ingredients that might be related to each other. So if I just go back to this original slide here, so example where I've got cherry tomato, and this splits out into cherry or tomato. The idea here is that if I have beef tomato, then the tomato bit of beef tomato will refer to this node here. And same as if I've got glacy cherries, the cherry bit of that will come onto here. So effectively, we're building in these connections between the data, and what we can start to think about is, well, we've added these extra connections in. How can we leverage that graph structure to be able to find out more information and more potential entities that are the same entity or candidates to be identified as duplicates? So first thing we're going to have a look at is node similarity. And what we're going to be doing here, we're going to be effectively using ingredient name as our pivot point. We're going to try and compare ingredients together. And what we're trying to say is if there's a huge amount of overlap, so if you've got two ingredients and they've got many ingredient names that map together, the more of that goes on, more of those structures, the more likely that they are, that they are similar. And we're going to be using the Neo4j graph data science library for this. So I'll show you some of the graphs. And one of the functions we're going to be using is node similarity. Something to bear in mind, and why I've pulled out this graph is, and we'll go through an example of this, is to use the graph data science library. It's recommended that you load in memory the graph that you want to process. And this means you can run the algorithms very efficiently. And it's a great way of being able to shape your graph based on the algorithm you want to run without having to make physical changes to the graph on your database. And so one of the structures we're going to be loading into memory is this bipartite graph. And it's bipartite because I'm using two different node types in this situation, or it could be more. So, and this is effectively, like I said, we're using ingredient name as a pivot point to sort of see how other ingredients compare to each other. So comparing by ingredient name. The next thing we're going to be looking at, again, to leverage the graph structures, is we're going to use a community detection algorithm to try and group these ingredients together. And what we're going to be doing, the first step that we did, the node similarity, we're going to go through, and when we identify nodes that are similar based to a threshold that we've specified, it's going to create a relationship between those two ingredients. So, for example, almond flakes and flaked almonds, it'll create a relationship between those two, and I'm going to give it designation of similar to. And then what we're going to do is we've put in those structures. So we're using node similarity to build out some additional helping structures in our graph. And then what we're going to do is we're then going to put another memory graph. So again, we're going to another graph in memory. So again, we are going to reshape the graph according to the next algorithm we're going to run. So we're going to be running Louvain community detection. And the graph that we're reshaping to bring into memory is this monopartite graph of ingredient, and we're effectively pulling in ingredient similar to ingredient. So that's the graph structure that we're interested to bring in. And what Louvain community detection basically does, it looks at how nodes are connected to each other, and it tries to pull together densely connected nodes together into communities. And the idea is once that process is run, it'll say that a node that belongs to a community is the best fit for it, rather than if it was randomly assigned to another community. So those are the two algorithms that we're going to be running on our graph. And again, we're leveraging those structures that we have from the initial cleanup, the new structures that we put in when we run node similarity, and then we're going to pull some communities out. So let's have a look at this in action. So just to make you aware, so what I've done, so this data is already loaded into Neo4j. I've already done some of the cleaning steps, but I'll talk you through what's happening. So just as a rough idea to see how many ingredients we've got something around, I think it's 3,070 ingredients. So the first phase that I went through and go through this data is to just try and do some cleaning up. So for example, this query here is trying to go through and fix any of the encoding issues that I've got in the data. There's probably a cleaner way of doing this, but this is one approach that I used. So this is going through and cleaning the data. And then same idea, I want to try and deal with any errant characters. So for example, I want to get rid of things like just dealing with any brackets or dealing with quotes or that kind of thing. So just trying to standardize that, because there may be different ways that people are representing or accessing or using possession. So there may be varying levels of grammar as how people have been submitting recipes in there. So we're just trying to deal with that. So these are a couple of cleaning steps that I'm doing. And then the next step that I want to do is I want to start thinking about tokenizing those ingredients. So what we've got here, so we're matching all of the ingredients in the database. I'm turning them all to lower. So I want to get rid of any issues with capitalization, and then I'm going to be splitting them by space. So I'm now tokenizing each of the items. So here, this is effectively looping through all of the items that I've now split, and it's going to create new nodes. And notice that we're using merge here. So the idea is we want to have unique ingredient name points. So if it already exists, we're not going to create a new one. So something to bear in mind. So I've done a few splits here. I've not updated this yet. So prior to, I believe, 4.0, actually, no, I think it may have come in a later version of 3.5.x. A change in Cypher was made. So what you can do now is you can provide an array of characters that you want to split by. So you don't have to run split multiple times, which is what I've done in this example. So I will update the blog post, which I'll give you a link to, which this is based on, with the updated splits. So I'm going to tokenize by space. I'm going to run this and let that go. And because we're going to be doing a lot of stuff on ingredient name, I will create an index. So I'm going to let this query run first, and then we shall do the next part. Excellent. So I'm going to create an index, which will make the all the other queries run faster. You could have done index before the process I ran, which probably would have made more sense. So the next thing I'm going to do is I'm going to deal with all of those hyphenated words. So again, if we use the new version, the new sort of array of characters, we can use that to split. So anyway, I'm going to just quickly do that. And just a quick thing to flag what I'm doing here. So I'm doing the same approach here. And what I'm trying to do as well is this detach delete I. I'm trying to also just quickly see. Yeah, so this is to deal with this situation where this is to deal with this situation where you've created an ingredient name that's got a hyphen inside it, and we don't want to keep the ingredient name with the hyphen and the two new ingredient name nodes that come off. So what's going on here is we're finding out the original ingredient name. So it's component of in. So this is the original ingredient name that's got that hyphenated word. We're doing the split, and then we're remapping the new split items back onto the ingredient, and then we want to get rid of the original ingredient name that has the hyphen. So that's what's going on. We're just sort of cleaning up here. So we'll run that. And the next couple of things we're going to do is we want to get rid of, what we want to do is get rid of any stop words, anything like and, the, this, with. I also want to get rid of words like so, to, because I'm making the assumption, and this is like a domain specific assumption, that anything that's 2 characters or fewer is not going to be an ingredient name. It's probably going to be a stop word or something like that. And the thing to bear in mind as well, these are all the ingredient name components. So the idea is it doesn't matter. We're using these to create structures in our graph. So it may not be a problem if we lose one, because we're interested about all of the other ingredient names that map and cross over. So this is a relatively safe assumption to make for my use case, given the domain and the business rules that I've specified. So I'm going to do this and get rid of those ones. And then the meaty ones. So next one we want to try and do is deal with the plurals. So if you think about that, there's going to be a number of ways that you have plurals. So we're going to have things like things ending with S. So those are the straightforward ones. We also have words typically that end, if the word ends with a vowel, then the plural might be ES. So you think about tomato and tomatoes as an example. And you also have things modifying with OS. So again, this is a bit of a messy way of us trying to go through and deal with those plurals. So effectively what we're doing is quite an expensive query here, where we're trying to bring back basically 2 pairs comparing every single ingredient name against every other single ingredient name in the database. And we're just trying to compare, and if it turns out that they match, then we're going to get rid of one of those. So this is how we're trying to do it with the plurals. So that's an example. So let's run that. And as you can see, we're starting to use more fuzzier and fuzzier approaches to deal with some of the to deal with cleaning this data and getting it ready. So next thing we're going to do here is we're going to do some fuzzy matching based on the word length, similar words. So Levenshtein distance is a very common one for using this. I've decided to use Sorensen dissimilarity. So again, this is going to check the words based on the threshold that I've provided here, and it's going to go through and do the fuzzy matching. And again, this is trying to deal with tenses and any plurals. And again, any sort of spares, we're going to get rid of those ingredient name nodes. So this will take a little while, as it is quite an expensive query. So what we're effectively doing is, again, we're doing this sort of query where we're trying to pair every single different instance of where you've got two ingredient names and doing that comparison. For those of you who are going, hey, I want to use Sorensen dissimilarity, that sounds brilliant, that's available in the APOC library. So if you're using Neo4j desktop, you can add that via the plugins. So that's one of the APOC functions that we're using here. And another APOC function we're going to use is double metaphone. So this one here, we're looking at the structure of the words, and we're using a specific length. And this is basically having a look at, you know, is there a letter or so out, and based on ratio, and then saying, well, those are similar, and it's going to get rid of those. Another thing we can do, which I use here, is I use double metaphone. And what it's going to do is we're using Sorensen dissimilarity to try and reduce the number of items we're going to use with double metaphone, because again, this is quite expensive. So we're going to filter out some of those. And then double metaphone is basically trying to find out if two words sound the same. So the spelling might be different, but do these two ingredient name components sound the same? So for example, you might you think about like a ton. So you may spell ton as T-O-N, or you may have ton as T-O-N-N-E, but they both have the same sound. So in this example where it would class those as both being the same. So that's what this is going to do. And again, if it finds two ingredient name components that sound the same, it's going to get rid of one of those. So we're now going to run this one now, as the last one has completed. And okay, so we're going to let this run, and then we're going to have a quick look at just by carrying out these various cleaning steps, we're going to have a look at how many duplicate ingredients have we found. So we're going to let this run, and I'll quickly talk you through what's going on here. So, this is a very lazy query by myself. So effectively, we're going to go through the mapping. And yeah, actually, I think I'm going to step past this query now, because this is quite an interesting query. But what I'm basically trying to do, I'm using an intersection and the buffer to join through and see which ingredients join together. So what we're trying to One moment, I think I've missed something off my query. I shall check what I've done there. So basically, what's happening in this query is it's starting from ingredient name, but what we're trying to do is we're trying to find all of the ingredients that have exactly the same number of ingredient names between them. So this is like 100% intersection. So we don't want to have this one's got 3 out of the 4 names and this one's got 3 out of 4. We're literally just saying exactly the same. So this is basically trying to say, what if we linked together? So let's just quickly sort that by name. So let's do collection. So you can start to get an idea of what's happened. So this is just by getting rid of the sort of any characters, any sort of words that are two or fewer characters. We're getting rid of stop words. We're getting rid of plurals. We're trying to ignore word ordering and that kind of thing. So you can see just by doing that data, just doing that initial cleaning and things like that, you can see straight away we're identifying, we're being able to identify and get rid of a lot of potential duplicates. So you can see here, so garlic and ginger paste, you can see with our sugar. Great one here where we can see an example of where we've gotten rid of stop words. So we've got corn cob and corn the cob. Again, so just by doing that data cleaning, we've got this like really sort of great data set, and we've already, you can see an example here. So 348, so you can see how many potential duplicate groupings we've discovered by doing this. So we've done that great piece of work. So let's, okay. Right, so what we can do next is we're now going to use node similarity to try and find based on these intersections. So bearing in mind this is like an absolute match, so both of these ingredients got an absolute same ingredient name components. What we're going to do now is we're going to use node similarity, and it's kind of going to do the similar thing, but we're giving it a cutoff. So it's going to be looking at the structure and comparing the intersection based on the ratio of those ingredients. And what it's going to do is that all the ingredients that meet a specified threshold or a cutoff, it's going to create a similarity relationship between those two ingredients. So we're going to be using the graph data science library. So what we need to do is, or what I'm going to be doing here, is I'm going to be creating an in-memory graph, and this in-memory graph is going to be exactly the structure that I want to be able to run this algorithm. So you call it using this GDS graph create Cypher. So again, if you're using Neo4j desktop and you want to install graph data science, again, you click on the plugin option and it will add the graph data science plugin. So I'm going to give it a name. So I'm going to give my graph a sensible name of similarity. And what you do is the first part, you say what nodes you want to use. So I'm using the Cypher, the Cypher query. So I'm using Cypher to form what my graph is going to look like. It'll also do it direct load from disk. If you know that everything in your database is going to, you can pull up all of the labels or all of the relationships. So you've got a number of options. So have a look at the graph data science documentation. There's a link to that at the end of this presentation. So what I'm doing here, I'm creating my bipartite graph. So what I want to do is I want to match all of the nodes that are either ingredient or ingredient name, and I'm going to return the IDs for that. And the next part, I'm declaring what relationships I want. Also, I'm saying how these connected that I'm interested in. So I'm interested in ingredients being connected to an ingredient name. So I'm returning those back. So I'm going to go off and create that graph. Oh, I've been a bad citizen and I've forgotten to clean the graphs. Okay, cool. Right, so I'm going to create my graph. And then I'm going to run node similarity. So here it is. Again, you call the function GDS name of the algorithm. And something to bear in mind is the structure is very ordered when you call the graph data science algorithm. So it's always in this pattern of GDS dot name of the algorithm you want to run dot what do you want to do. So write is it'll write back to the graph. You've got a stream, it will stream the results out. You've got stats that will give you statistical information about what's going to happen and so forth. So it's always in that same format. So I want to write stuff back to graph because I want to write those relationships between similar ingredients. And I've got, my graph is called similarity, so that's what I'm going to call it. This is my similarity cutoff. So this is the, I'm saying I want a cutoff of 0.8. So what I would suggest is go and have a play with the different cutoffs. So if you've got time, I'll have a go and show you what happens when you use different cutoff values, and you can start to see the impact on the ingredients. I want to write a relationship, so that the relationship type is going to be similar to, and I want to write a score as well on the relationship. So that's something we can do as well. In fact, what I could probably do is I could drop this and, oh, do we want to freestyle slightly? We'll leave it for now. So basically, this is what I'm going to do. So I've got this cut off that. So I'm now going to run this algorithm, and it's going to run that function. So let's have a quick look at what it has done. So I'm just basically saying here, using that similar to this new relationship that's over done. So this is going to basically link all the ingredients that met that threshold whilst doing no similarity. I'm going to collect the names, and I'm going to order them by size. So basically, which ones have been tagged together? Most of them are similar. Excellent. So I start to get an idea. So have we got some fun ones? So yeah, so here you go. Here you've got a great example one. You've got the skinless boneless chicken breast fillet, and you got like boneless chicken breast fillet. So it skipped the skinless, and then you get boneless skinless breast fillet. So you kind of get the idea. So you can see it's starting to do this thing where it's dealing with that extra word, because there's enough commonality about those groups that it's fine and it meets that. So we've done that. So as the next thing, let's try and join these two communities now. So I'm going to do another in-memory graph. I'm going to call this one community. And what I'm doing now, so this is now a monopartite graph that I'm going to now store in memory, because we're only using one label. And the one label we're using here is ingredients. And what we're going to do is we're going to leverage those structures that we've added to the graph with the previous algorithm that we've run. So I want to load up all ingredients. And I'm interested in how ingredients are similar to other ingredients. So I'm using that connection there. So we're going to load that up into memory. And then I'm going to run the Louvain community detection algorithm. So what's happening here? So you'll notice here, I'm not using a write, I'm using a stream. And I'm doing this because actually I wanted to create an external node, and that node is going to have the community ID. And I want to link the ingredients off of that community node. That's how I've chosen to do it. What you can do when you can write the properties of the nodes and what community they belong in, but I prefer to have a separate node. So you have that flexibility as well. So I'm calling the Louvain algorithm. I'm yielding the node ID and the community ID. So node ID is going to be the ID of the node. Community ID is the community identifier that node belongs to. I'm basically turning that ID into a node now, or it's going to return me the node, but community ID. And then what I'm going to do is create an entity, which is going to be my community. So I'm merging that. So if it already exists, don't create it again. And I'm going to merge that entity contains a member of I. So I'm going to run this. And once that's completed, we're going to have a look at some entities in here. So effectively, what this is doing is saying, match the entity that has ingredients, and then I'm going to return the entity ID. I'm going to collect all of the ingredients associated to that node, and I'm just going to order those based on the communities that got the most number of ingredients. So there we go. So you can see now it's started to join these together. So we can see we've got one community with the chicken, we've got another community with the garlic and ginger paste, and so forth. So you can start to see what we've been able to do to group these things together and group the ingredients. And what we can do as well is if we wanted to drop the threshold quickly, so we've got a couple of minutes, so I'll quickly do that so you can get an idea of what's going on. So I'm going to get rid of those two memory graphs. I'm going to delete the entity and the similarity relationships. I'm then going to recreate the the similarity graph. I can probably, with for sake of completeness, we shall do it like this. Then going to run this, and I'm going to drop the threshold down to 6. And then I'm going to do these both again. So that's going to, so we're repeating that, but what we've done here is we've dropped the similarity threshold. So what I could have done, so this is still in the same setup for when I was still using the predecessor to graph data science, which is the graph algorithms library. So what I could have done is if I'd written all of the results from here as the score, then I could have just reloaded the community graph. So again, that's something we'll update later. So let's run this. So this will probably take a few seconds. It's pretty quick. Cool, and just as a comparison, so I forgot to drop the thing. Okay, sorry, I forgot to drop the threshold, so we're sure. Oh no, I did, it's cool. So you can see an idea. So I dropped the similarity threshold, the thresholds, the cutoff for the node similarity. So you can see what we've got now is we've got much broader sort of groupings of things together. So you can see all the flowers together, all sugars together. But what you might find is things like sugar syrup and these things are joining together. So you have to bear in mind when you're using these and you're working with the thresholds about the dangers of either the thresholds are being set that you overfit your data. So this is where you've picked a threshold that fits the test data that you've used, but it doesn't give you the expected results when you use it later. And the challenge around underfitting your data, where your threshold is, your threshold is really, really high, and you can inadvertently miss some results. So that was very quickly going through that. And so we've got a couple of links as well. So this is all based, if you want to read through this and have a go yourself. The blog post that I've been referring to is this one. So it's a Medium article. It's got a very long link. So this is why I've given you the shortest one here. If you're not using Neo4j desktop but using Neo4j server and you want to download the Graph Data Science library, you can get it from the download center. And you've also got the documentation here for the Graph Data Science library, which gives you an explanation of each of the algorithms does, and it gives you examples about how to execute them, how to load your memory graphs and that kind of thing. And one thing I will mention before we go, don't forget to clean up your graphs after you finish. So generally it's recommended that you only have one graph memory. I was a bit naughty because I know my data is quite small, so I used 2 so I could quickly switch between them. But do clean your graphs after use.